So we are continuing with Chapter 4 and learning more reactions. What I would continue to do throughout this chapter is, as you learn a new reaction, make a flashcard, add it to your study guide. I think the most challenging part of this chapter is being able to look at your reactants and predict the products. So that brings us to acid-base neutralization reactions. And it's also considered a double displacement reaction, and we can see why. So what we're looking for is an acid. So we learned a list of strong acids that we need to know, like hydrochloric, hydrobromic, nitric, sulfuric. Those are ones that we need to know. And then any metal hydroxide, the hydroxide is what is going to make it basic. So if we look at the reaction of hydrochloric acid with sodium hydroxide, we see that the hydrogen pairs up with the hydroxide to form water, and then the sodium pairs up with the chloride to form sodium chloride salt. So it's still a double displacement reaction. The same rules are going to apply with the molecular, total, and net ionic equations. So it's also going to be important to write the state of matter. So the hydrochloric acid would be aqueous, sodium hydroxide would be aqueous, we're forming liquid water, and then the sodium chloride is soluble in water. It would also be aqueous. So some things that we want to remember and why we're writing these total and net ionic equations is because when we put strong acids like hydrochloric or strong bases like sodium hydroxide into water, they completely dissociate. So they break apart into ions, and this hydrogen that we get, this H+, that is what makes it acidic. So again, for strong acids and bases, it's going to completely split apart or dissociate into ions. And then when we have something like an acid that dissociates and forms H+, this H+ then pairs up with water to form H3O+ or hydronium. So when we're referring to the concentration of acid, we're referring to H+. Hydronium is pretty much referring to the same thing. So I just wanted to give you some examples of acids and bases. And we have a few definitions, and we will flush those out a little bit later. You also have a sheet that tells you about different types of acids and bases. But for our purposes in this chapter, an acid is going to produce H+, so it's an H+ donor. And then a base is going to produce OH-, or it's going to accept H+. Okay, I want you to just keep in mind though that there are other types of acids and bases, so this is not the full definition of it. Okay, something to keep in mind is that water can act as an acid or a base. So something we know about water is that it has lone pairs of electrons that we will talk more about later. So water can do some interesting things. We have different types of acids. So a monoprotic acid is one that only has one H+ to donate, like HCl or HBr or nitric acid. And then we also have polyprotic acids, which have more than one H+ to donate. So a good example would be sulfuric acid, or if we have H3PO4, phosphoric acid. And here are some everyday examples of acids and bases that we see. So we have other types of reactions that are gas-forming reactions. Okay, so we've already seen acid-base in general, where we have strong acid plus metal hydroxide gives us water and salt. We have some other types of reactions that are still considered acid-base reactions, but they're even more specific, and they form different types of gases. Okay, so I would, if you're adding to your flashcards or your list, make these specific and give them their own flashcard or own space in your list of reactions. So let's go through this and see what we're looking for. Okay, so if I take a strong acid and I am reacting it with something like a sulfide, so some metal sulfide, doesn't matter what this metal is, I am always going to form a salt, okay, plus hydrogen sulfide gas. So this is the gas that we form, right? For a lot of these we have some unstable intermediate, so you have something form and then it breaks down into something else. That's not the case for the hydrogen sulfide forming. So what we're looking for is metal sulfide and strong acid, and this is what we get. The next one is going to be where I'm looking for either a metal carbonate or metal bicarbonate. So essentially, if you see carbonate in it and you're reacting with strong acid, then you do actually form an unstable intermediate. Let's draw an example below. So if I have something like sodium bicarbonate or baking soda, and I react that with hydrobromic acid, okay, let's look at what I initially formed. So again, this is going to be a double displacement reaction. So the sodium pairs up with the bromide, so I get sodium bromide that I know is soluble in water, and then this H pairs up with the bicarbonate. So H has a plus charge and then the bicarbonate has minus, so that makes sense. And what we get is carbonic acid. Okay. But carbonic acid is going to be something that is unstable. All right. So what I actually produce after this carbonic acid breaks down is this turns into carbon dioxide and water. All right. So what I really get out of this reaction is sodium bromide, that's aqueous. I get, let's put a plus, water, that's liquid. And then I also get carbon dioxide gas. All right. And then if I think about now breaking this down into my complete ionic and net ionic equations, that's something I would practice. Remember that these break apart because they are aqueous. This breaks apart because it is aqueous, but the water is a liquid and the carbon dioxide gas, those stay exactly as is. We don't split those apart into ions. So that's something I would practice. Let's go through the list. So the next thing I'm looking for is a sulfite. Okay, if I take any type of sulfite, so metal sulfite, metal bisulfite, and I react that with acid, then I am going to get initially this acid, okay, so sulfurous acid, but then it's unstable, so it breaks apart into SO2 and water. Okay, so I get SO2 and water. So seeing these products where I have three different products, it may not initially look like a double displacement reaction, and that is because I formed something initially and then it breaks apart because I formed something that's unstable. The next one I'm looking for is an ammonium salt. So something like ammonium chloride. And this time, instead of reacting with acid, I need to look for a base. As soon as I see a base, that means I am initially forming ammonium hydroxide, but this breaks apart and it turns into ammonia gas and water liquid. Right? Again, for all of these, it's good practice going back and writing your complete ionic and net ionic equations. So here's some practice, and we want to see what types of solutions we have. So let's go ahead and look at this. Phosphoric acid is one of our strong acids that we need to know, and we have a metal hydroxide, so we're doing an acid-base neutralization. The hydrogens are going to pair up with the hydroxide, the lithium will pair up with the phosphate. And remember, our first step is to write the correct formulas on the other side. So if my lithium is pairing up with phosphate, I need 3 of those to pair up with the phosphate, and this is soluble in water. Okay, and then my hydroxide we said is pairing up with the H plus to form liquid water. Okay. One quick way to balance these when I have an acid and a hydroxide base is for every H plus, I need to react with an OH minus. Since I have 3 H pluses here, I need 3 OH minuses here. Every H plus that pairs up with OH minus forms a water molecule. So I am forming 3 water molecules. That's a quick hand way to balance that. Let's look at what we have next. I have an ammonium carbonate and I have an acid. All right, so I have a carbonate and I have an acid, which tells me this is one of my gas forming reactions. So again, I am going to have, we have the H pairing up with the carbonate, we have the ammonium pairing up with the nitrate. So initially what I get is ammonium nitrate, which is soluble in water, plus we get carbonic acid, okay, which is also soluble in water, but this is unstable, so it breaks down. So what I really get is ammonium nitrate, that's aqueous, and I get water, liquid, and carbon dioxide, gas. So I will leave this to you to go ahead and balance, right? And again, good practice is going back and writing the total and the ionic equations. Let's look at what we have for this one. I have acid. We know this is a strong acid, and I have a metal sulfide. Okay, so again, the H is going to pair up with the sulfide. The magnesium will pair up with the bromide, and what I get on the other side is magnesium bromide, that's soluble in water, and then I'm forming hydrogen sulfide gas. So this one doesn't have an unstable intermediate to worry about. And I'll leave it to you to go through and balance the equation. And we should get this. So let's look at a sample problem. So we have a 10 milliliter sample of an unknown phosphoric acid solution, requires 112 milliliters, and we're given the concentration of the potassium hydroxide to completely react with it. What is the concentration of the acid solution? So the first thing I say is, well, I actually have a chemical reaction. So before I do anything else, I'm going to write that out. What we have is potassium hydroxide solution, and we are reacting that with a phosphoric acid solution. Okay, we have acid, we have metal hydroxide base, so we know we're forming water, and we are also forming a salt. Okay, and let's also make sure we put liquid here. Now for this, we can go ahead and balance it. We have a 3 here, so since we have 3 H pluses, we need 3 OH minuses, and we're forming 3 water molecules in this. And just like we did in class, let's go ahead and fill out the information we have. We have 112 milliliters of this, and we have the concentration, molar. We have 10.0 milliliters of this, so this is what we currently have. And what we want is we want to figure out the concentration of the phosphoric acid solution. So essentially it's a titration, and we know that concentration is units of moles per liter. So that's what we want to figure out. And if we think about it, we already have the volume of the phosphoric acid solution. What we really want to focus on are the moles. Let's fill out our get there. So we know that we have a concentration for the potassium hydroxide, so let's put that in. We have 0.100 moles of potassium hydroxide for every 1 liter of the potassium hydroxide solution. We also know, again, that the big M stands for moles per liter, and that's what we want. We already have the bottom, so what we really need to figure out is the top. And we currently have milliliters here and here, so we know we're going to also need that we have 1,000 milliliters in every 1 liter. Okay, so I think we have most of what we need to start our problem. Let's do a roadmap to make sure. We're starting with milliliters of the potassium hydroxide solution. So I'm putting aqueous to indicate it's the solution. We are starting right here with what we have. What we can go to next is liters of the potassium hydroxide solution. And from there we can use the concentration to go to moles of just the potassium hydroxide. And from there we can use our balanced equation to go to moles of the phosphoric acid. Okay, and then from there we can figure out the concentration of the phosphoric acid. So let's focus on just the moles for right now. Let's plug in what we have and follow our roadmap. We have 112 milliliters of the potassium hydroxide solution. So again, we want to label everything. We know that we have 1,000 milliliters of the potassium hydroxide solution for every 1 liter of it. And from there, if we follow our roadmap, we can go to moles. So we want liters on the bottom, 1 liter of this potassium hydroxide solution. And on top, we want our concentration, which is 0.100 moles of potassium hydroxide. Sorry, it's a little bit slanted. So now we have 3 moles of potassium hydroxide on the bottom for every 1 mole of the phosphoric acid on top. So if we plug that into our calculator, what we get is 0.003733 moles of the phosphoric acid. Okay, so we're not done yet because we want concentration. We want the big N molarity. So we're going to take the 0.003733 moles of the phosphoric acid, and if we want moles per liter, we need to divide by, we know the volume, we just need to move the decimal so it's in liters. So we have 0.010 liters of the solution. Okay, and again, I got this from the fact that we have 10.0 milliliters that was given to us up here in the problem. So if we go ahead and calculate that out, we should get this for our concentration. So that brings us to acid-base titrations, and that's exactly what we did. So it's a method used to measure an unknown amount of acid or base, or an unknown concentration of it. And it has many applications. So in the food industry, if we're thinking about biodiesel waste, aquariums, making sure the acidity is adjusted properly. And the general way you do it is you have an acid with an unknown concentration in your Erlenmeyer flask. In your burette, you have a base solution where you do know the concentration, and you can figure out how much volume you used of that specific base solution, and you already know the concentration, and here you know how much acid you measured out, so you can figure out the concentration. You can figure out how much you used of this base solution. Okay, and this is what it looks like. So just some terminology, and we use a phenolphthalein base indicator, right? And the equivalence point is where the moles of acid, H+, are going to be equal to the moles of OH-, the base. But what we see is the end point where we make it ever so slightly basic, and as soon as we do that, we see this pink color. So this has gone way too far. We're looking for a very faint pink color. So something else you can look at is red cabbage. So this is if you have kids or you have nieces or nephews, brothers and sisters, this is a really fun activity to do. But it turns out that red cabbage has an organic compound in it that is a natural indicator, an acid-base indicator. And what you can do is you can boil up some cabbage and then strain it, and you can use the juice to test different household items. So based on the pH, the indicator will make it change into these different colors. So this is a really fun one. When my daughter is old enough, we're definitely going to do this. So here's another problem that I will leave you with. So you can try this one on your own, try setting it up, and then we'll talk about it. All right, so it's a similar titration problem. We have sulfuric acid. We're titrating with a potassium hydroxide solution. You're given the amount of base that's required to reach the equivalence point, and you're trying to figure out the concentration of the sulfuric acid. So very similar to the way we set up the previous problem. And you should get this answer. So our last class of reactions are redox reactions, oxidation-reduction reactions, and it encompasses a lot of different reactions. So you definitely want to be organized and know that which reactions are redox reactions, but also still being able to predict the products of those reactions. So a lot of everyday things that we see are redox reactions, and essentially what it is we're shuttling electrons. So something's gaining electrons, something's losing electrons. We see it in batteries, a combustion reaction, so the reaction that happened when you drove today in your car to turn your fuel into energy that pushes your car along, that's a combustion reaction, it is redox. When you see bananas turning brown, it is also a redox reaction. So a little terminology, right? All redox reactions are going to involve the transfer of electrons, all right? And if we think about why this happens, it goes back to things that we've seen before. We want to gain and lose electrons to become stable. So metals like to lose electrons to become stable, and nonmetals like to gain electrons to become stable. All right, so I have two silver atoms that are each losing an electron, and then sulfur gains those 2 electrons, and now everyone is happy, everyone's stable. Right? So we say that silver is oxidized because it's losing electrons, and sulfur is reduced because it's gaining electrons. And I still remember Leo the lion says grr. I think it's way better than oil rig. Okay, so again, we have the silver is being oxidized. It's going from silver that is neutral to silver with a plus charge, and then our sulfur is being reduced. It is going from sulfur that's neutral to sulfur with a negative charge. The substance that's being oxidized is called the reducing agent. The substance that's being reduced is called the oxidizing agent. So make sure you get those straight. It's easy to confuse them. So how do we recognize a redox reaction? And what we need to do is do something called assign oxidation states. So in order for a redox reaction to occur, I have to look at each element on the reactant side and on the product side, and the oxidation states have to be changing. Okay? So we have some rules, and something we want to keep in mind is that an oxidation state is not a charge. An actual charge, it's a hypothetical charge. It assumes that the most electronegative atom has all the bonding electrons. Okay, so it's a hypothetical charge, right? But here are a few rules. The oxidation state of an atom and its free as a free element is 0. Okay, so if I have platinum or rhodium or iron, just by itself as a metal, its oxidation state is 0. But it also includes our diatomic elements. So if I see something like Br2, O2, nitrogen, and so on, those will also have an oxidation state of 0 because it's in its elemental state. The oxidation state of a monatomic ion is going to be equal to its charge. So if I have something like iron 2+, then the oxidation state is +2. The sum of the oxidation states of all the atoms in a neutral molecule must be 0. So it's very similar to the way we assign charge. If we have an ion, the sum of the oxidation states has to be equal to the charge of that ion. And the last thing is, if we have to give priority when assigning oxidation states, here they are. So group 1A and 2A, so group 1A will always be +1, group 2A will always be +2, and then you have a few more in order, right? But I think the best thing to do is to go through and assign some oxidation states. So all of the ones on the top are neutral, which means when we assign the oxidation states and add them up, overall has to be neutral. So oxygen is the one that gets priority in this case, and its oxidation state is going to be -2, right? Which means the nitrogen has to be an oxidation state of +2 to balance it out, right? For this one, we have an oxidation state, again, of -2, but we have 2 of them. So overall on this negative side, we have -4, which means that the nitrogen has to be +4 to balance it out, okay? For this one, we have the oxygen is -2, and again, we're assigning oxygen first because it gets priority, which means overall on this side has to be -2, which means each of those, because I have 2 of them, has to be +1. Okay, so nitrogen can have different oxidation states. So now let's look at the ones that have charges. So now when I sum up the oxidation states of the elements, it has to be equal to whatever this charge is. So again, let's go through. We know the oxidation state is -2 for oxygen. Okay, it has priority over sulfur. And I have 4 of them, so total here I have -8, which means this sulfur has to be +6, so that way when I add those two up, I get -2. Right? Here I have -2 oxidation state for oxygen, and I have 3 of them, so I get a total of -6. Hydrogen is always going to be +1, so if I sum these up and I need it overall to be -1, that means that this sulfur has to be +4. That way I get 5 minus 6. So the oxidation state is +4. If I look at the last one, for oxygen, again I have -2, but I have 7 of them, which gives me -14. Okay, to be overall -2, that means that this total both need to be +12, but I have 2 chromium, so I need to divide by 2. The oxidation state of each one is going to be +6. Okay. All right, so the last thing we want to do is balance redox reactions. And we have 2 different types. We have ones that don't involve oxygen. Okay, so the ones that don't involve oxygen are a little bit more straightforward, and then we'll go back to the ones with oxygen. So we want to identify what element is being oxidized and what element is being reduced first. So if we look at the aluminum, it's going from oxidation state of 0 to +3. So 0 +3. We have iron going from +2 to 0. So now if we want to see what's being oxidized and what's being reduced, we are losing electrons from the aluminum. So Leo the lion, if we're losing electrons, that means we're being oxidized. And then for the iron, since we are gaining electrons, we are being reduced. Right? So the next thing is we can split it into half reactions. So when we split it into half reactions, we're going to take the aluminum as a solid is going to the aluminum with a 3+, and then we have the iron with a 2+, going to iron that's a solid. Okay, so the next thing we want to do is add in electrons to the half reactions so that we get a charge of 0 on both sides of the equation. So we need to figure out what side we're adding electrons to, right? So in this case, we are adding electrons onto this side because this is neutral overall. We have a +3 here, so we need to add in 3 electrons, right? On the bottom, we have 0 overall charge. On this side, we have +2. So on this side, we need to add 2 electrons to balance out the +2. Okay, so we have that. The next step is we want to multiply one or both equations or reactions, the coefficients, by the appropriate number to make the number of electrons in each half reaction the same. So if we go back, we have 3 electrons here, we have 2 electrons here. So I need to multiply this whole thing by 2, and I need to multiply this whole thing by 3. Okay, and I'm going to write it down here. We have 2 aluminums, and it's going to 2 aluminum 3+ aqueous, plus we have 6 electrons. Here we're multiplying by 3, we have 6 electrons plus 3 iron 2+, and we're going to 3 iron solids. Okay, one thing we should get is that the electrons should cancel because the aluminum is giving up electrons, the iron is gaining those electrons. So we want them to cancel out, and what we get is 2 aluminum solid plus 3 iron 2 plus is going to 2 aluminum 3 plus 3 iron solid. So that was our last step. Cancel out electrons and combine the half reactions again. So you have another example, so you can pause the video and work through this example on your own. So now we have the redox reaction where we have oxygens involved. So now we need to start adding in waters and H plus to balance things out. So again, we're going to identify what element is being oxidized and which one is being reduced. So here we have an oxidation state of +2, right? Here we know that each of these oxygens is -2, and we have 2 of them, so the total will be -4, which means lead has to be +4 to balance it out. Okay. For the iodine, it's -1, whatever the charge is, and here, since it's in its elemental state, it is 0 for the oxidation state. So I'm going from +4 to +2, which means I'm gaining electrons. I am being reduced. And then here I am going from -1 to 0. I am losing electrons. I am being oxidized. The next thing we want to do is split into half reactions. So I have lead oxide, and I am going to lead with a 2+ charge, right? And then my other half reaction, I have iodide ions, and I am going to the elemental form. Okay, so the next thing I want to do is balance the non-oxygen, non-hydrogen elements first. Non-oxygen, non-hydrogen. So I have 1 lead, I have 1 lead. I have 1 iodine, I have 2 iodines. So I need to add in a 2 here. Okay. Then we're going to balance the oxygen by adding in water, followed by adding H plus to balance the hydrogen. All right. So let's do that for each one. We want to balance the oxygen first by adding in water. We have 2 oxygens here, which means we need 2 water molecules on this side. So that way we get 2 oxygens. But now we have 4 hydrogens. So on this other side, I need 4 H plus aqueous. In this one, we are already balanced because we don't have any oxygens or hydrogens to worry about. So let's look at the next step. For each half reaction, add electrons on one side to balance the charge. So the overall charge on each side of the equation is equal. So let's go back. I think it's easier to start with the bottom. So the overall charge on this side is 0, and the overall charge on this side is -2. I have 2 iodides, each with a -1 charge. If I'm adding in electrons, they have to be on this side. So plus 2 electrons. Now I have a -2 charge on both sides overall. All right. Let's think about what we have on this side. I currently have +2. Water is neutral. And then on this side, the lead oxide is neutral, but I have 4 H pluses, so I have a +4, which tells me I need to add in 2 electrons on this side. So plus 2 electrons. Let's see what's next. Multiply one or both reactions, the coefficients, by the appropriate number to make the number of electrons in each half reaction the same. Okay, so if we go back, it turns out that I have 2 electrons here and I have 2 electrons here, so it's already balanced. Now let's say I had a different number of electrons. Then, like my previous problem, we'd have to multiply every single coefficient by some factor to make the number of electrons the same. That way the number of electrons I'm losing is equal to the number of electrons I'm gaining. Now in this case, since they're the same, we can go ahead and cancel them out. Okay, and assuming that this is under acidic conditions, I don't need to do anything else. I'm going to go ahead and do the last step, which is cancel out the electrons and combine the half reactions. So let's do that. I'm adding everything up on the reactant side. I have 4H plus aqueous, and I have lead oxide, solid, plus 2 iodide aqueous, and I'm going to lead with a 2 plus charge plus 2 water molecules plus iodine, and this is what I have in the end. Okay, so just as a last check, always make sure you have charge balance. Right? I want you to do this one on your own, right? So when you split it into your half reactions, you have the permanganate going to manganese oxide. You have the bromide going to bromate, so you'll split it into the two half reactions and do the same thing. Now that we have oxygen involved, we have to add in water molecules to balance out the oxygen, H plus to balance out the hydrogen. We have to see if we have charge balance to see where we need to add our electrons and go through the same process. Okay, so a summary of the types of redox reactions. And for redox reactions, since it encompasses so many reactions, there are a lot of them. A combustion reaction, so anytime you see a molecule that's only composed of carbon, hydrogen, or carbon, hydrogen, and oxygen, anytime we're doing a combustion, that means combining with oxygen, and I'm forming carbon dioxide and water. We could also have a combination or synthesis reaction where we're taking two smaller compounds and combining them to make one compound. A very common one is taking elemental or a metal and combining it with something like chlorine gas and forming a salt. Okay, and it is a redox reaction. If we think about it, sodium is going from a charge of 0 or oxidation state of 0 to a charge of +1 or oxidation state of +1 rather. A decomposition reaction is also considered a redox reaction. So there are many types. One that we're going to focus on quite a bit is a single displacement, and that is where I'm switching one partner instead of two. So if we look at this one, the magnesium is now pairing up with the chlorine, and hydrogen gets kicked out in its elemental form. So I form magnesium chloride, and I have hydrogen gas. Okay, and what I would do is go through and check the oxidation states to prove to yourself that this is a redox reaction. Another common example is if you take sodium metal and put it in water. Do not do this. So it is very, very exothermic. I'll show a video in class, but it forms sodium hydroxide, and that's why we can see it with the phenolphthalein that's added here, and it produces hydrogen gas. Okay, here's another example where we have now the potassium pairing up with the acetate, and then lead gets kicked out by itself as a solid in its elemental form. Okay, in order to figure out if these reactions occur or not, we have to use something called the activity series. Okay, so the activity series will always be given to you, and what we can see here is an ion can oxidize any metal above it. Right? So here's one example. If I have lead, right, it can oxidize any metal that is above it on the activity series. So it can react with tin, it can react with chromium, it can react with aluminum, but it cannot oxidize anything that is below it. So it can't react with copper or silver or mercury. So that's how we use the activity series. Another common thing you'll see is that it will ask if something will dissolve in acid. So we have acid here, H+. Okay, it will dissolve, or it's allowed to react with any metal that is above it. in the activity series, but the acid will not react with any metal that is below it in the activity series. Okay, and that's because as we go to the top of the activity series, these are more easily oxidized or more willing to give up electrons than the ones at the bottom of the activity series. So here are some examples, and all of these should be arrows. So we want arrows, right? And I'll go through the first one, and what we're doing is we're looking at nickel is our ion, or I'm sorry, we're looking at zinc is our ion,